Yeah, let me start by thanking the organizers very much for this, for the invitation to talk here. This has been a great couple of days, and I've really enjoyed my time here. So I'm going to discuss a paper that appeared on the archive last week with my really excellent PhD student Zoltan Lacko and my fantastic longtime collaborator Takahiro Nishinaka. Zoltan is obviously with me at Queen Mary, and Takahiro is at Ritsumeikan University in Japan. Indeed, I'm going to tell you about flowing from some RG flows that start with 16 Poincaré plus special supercharges and end up, after some relevant deformations, at theories with 32 Poincaré plus special supercharges in the IR. But before going into great detail about why we care about these particular RG flows out of all the many that we could study, I'll give you some motivation about what I hope to discuss, and also review some pertinent concepts like accidental symmetries in QFT. And then I'll move on to discuss the UV starting points of these RG flows, which are some weird non-Lagrangian, in all senses of the word, at least so far, 4D theories. And then I'll spend probably the bulk of the talk telling you about the simplest example of the RG flows we have. And depending how much time is left, I'll tell you about some generalizations, and I'll conclude with some comments and open questions. So the basic goal of this talk is twofold. So first, to try to find a more unusual way to construct theories with four-dimensional n equals to 4 supersymmetry. Usually the way that we construct these theories is rather boring. We take some free fields and we gauge some symmetry, and then we study the corresponding theory as we vary the marginal coupling. But I want to try to at least construct a more exciting, give you a more exciting way to construct n equals 4 theories. And the second goal is to try to find a more controlled set of examples in which to study this phenomenon of supersymmetry enhancement that people have studied for a long time but has received a lot of attention recently. So why do we care about these questions? Well, I think it's fair to say that a lot of the work in quantum field theory in the last 10 years has been to try to carve out spaces of consistent quantum field theories, whatever that means. And I think it's also fair to say that if there's one subspace that we could possibly understand fully, it would be the set of 4D n equals 4 theories, at least in dimensions larger than 2. So that's why we care about, or why I care about this first goal. The second goal, the reason I care about it, is that ultimately it would be very interesting if just given some UV CFT plus some specification of the neighborhood of that CFT, so plus some data having to do with the deformations and maybe a few other things, some anomalies or other such things, if you can predict when symmetry enhancement will occur, and especially when supersymmetry enhancement will occur. So obviously these two questions are extremely difficult, and I'm not going to give you, conclusive proof that the known space of n equals 4 theories is not complete, but I'll point out some interesting peculiarities of the theories that we'll construct that might have an explanation in the existence of some weird n equals 4 theories. Okay, so at a very lowbrow level, when we construct n equals 4 theories, what we do is we take some Lie algebra, G, and some n equals 1 vector multiplet, and some three adjoint chiral multiplets, and we gauge. And then we get some marginal coupling, and we study the theory as we vary the marginal coupling. Depending on where you go in this marginal coupling space, one description might be weakly coupled, or one might be strongly coupled, and there are dualities that usually relate these kinds of different descriptions of the same theory. But I should say that even in the context of n equals 4 gauge theories, the usual Super-Yang-Mills theories, there are a lot of subtleties that still haven't been worked out, even for the simplest case of G equals SU2. So even there, it's not entirely clear when you extend the gauge algebra to a gauge group and you specify the non-local operators that the theory has, it's not completely clear what is the full list of such theories. But I really honestly don't have much to tell you in addition to what these very brilliant people have said about this. So instead, I'm going to focus the discussion on trying to understand if it's possible somehow to engineer theories that differ from the usual Super-Yang-Mills theories by local operators. So since the theories that we're going to engineer from the renormalization group are so strange and being something built from the normalization group, you don't have full control over the infrared theory. It's useful to keep in mind, at least, what are the general features of n equals 4 supersymmetry that are independent of the existence of a Lagrangian. So, and I'm only going to study local n equals 4 theories. If you really want to be perverted, you could study non-local n equals 4 theories as well. By local, I just mean ones that have a stress tensor. And so if you want to study such a theory, then independent of the, then if the theory is something more general, something more exotic than the n equals 4 super Yang-Mills, there necessarily will not be a weak coupling limit. So in other words, whatever the marginal parameter is, it won't have an interpretation as a gauge coupling. It won't have the interpretation as taking some isolated CFT and gauging a global flavor symmetry of that isolated CFT. But whether there is a Lagrangian or not, as long as the theory is local, and maybe even if it's non-local, I don't have an argument in that case, but if the theory is local, then it always has an exactly marginal deformation, regardless of whether there's a Lagrangian, and this just follows from the work of Dolan and Osborne, and I think probably people in the 80s already knew it, that the energy momentum tensor of the n equals 4 theory always sits in a multiplet with something that you can deform the Lagrangian by preserving n equals 4. And of course, since the energy momentum tensor is not renormalized, then that coupling itself will be exactly marginal. Finally, a feature which might be somewhat less appreciated, I don't know, is that if you consider an n equals 4 theory Lagrangian or not, and you have a theory that has an odd dimensional vacuum moduli space, by which I mean at generic points, it's just a bunch of n equals 4 U1s, then necessarily there will be a global Witten anomaly for the SU2 for an SU2 factor inside of SU4R. What is this SU2 factor? Well, if I think of the n equals 4 theory as an n equals 2 theory, then the SU4R symmetry of n equals 4 contains in it an SU2 flavor symmetry from the n equals 2 point of view, and that SU2 will necessarily have a Witten anomaly because you'll have an odd number of doublets that are charged under that symmetry on the vacuum moduli space. And since the vacuum moduli space doesn't, at least the Coulomb branch from the n equals 2 perspective, doesn't break flavor symmetries, then anomaly matching guarantees that the UV theory must also have a Witten anomaly for this SU2 factor. So this is true whether the theory is Lagrangian or not. And so since we'll try to discuss this larger space of theories and some peculiar n equals 4 theories, it's just useful to keep these facts in mind. Yeah. 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 So this, in this case, it's just simply the case that there are an odd number of doublets under this SU2. So if you go to the moduli space, right, you have in the n equals 2 language, let's say you're on the Coulomb branch from the n equals 2 perspective.
So you're saying that this, the composition of this embedding of SU2 inside of
yeah.
SU4 would be such that only fundamental multiples show up, and it would be either an odd or even.
Yeah. If the vacuum and if the moduli space is odd, then it'll be an odd number. Even it'll be even. Exactly. Yeah. I have not, I mean, because I can, and n equals 2 is a more, I mean, there'll be manifest n equals 2 supersymmetry in what I'm going to say. I mean, so I might as well use as much supersymmetry as possible. Well, so here you start with an SU4, and SU4 also doesn't have a Witten anomaly. But there's an SU2 subgroup of SU4, and that can perfectly well have a Witten anomaly. It doesn't matter whether the SU4 group does or not. So, so how would we build such theories if they exist in quantum field theory? So one kind of modern approach would be to try to construct it via the bootstrap directly in conformal field theory. So that's a difficult task, though. It sounds nice, but what you have to do is you have to come up with a list of operators, and then you have to come up with a list of correlation functions, and you have to decide what your consistency conditions are on the correlation functions. And then you have to solve those consistency conditions. So, you know, in the case of conformal field theory, we know roughly what we should do. We should at least impose ward identities, and we should use crossing symmetry. But maybe there's more that we should do. But at least in the context of 4D n equals 4 theories, there's a very intriguing connection with chiral algebras due to Chris Beam, Leonardo Rastelli, and collaborators, and maybe by relating these objects, or some subset, some subspace of operators in the 4D n equals 4 theory to chiral algebras, as Chris Beam and friends do, it might be possible to use sort of the infinite resulting symmetry from chiral algebras to try to say something constructive at the level of CFT about these kinds of theories. Also, from this abstract perspective, it's sometimes useful to work out, correlation functions in the presence of defects, because then that gives you more crossing constraints and more fun stuff that you can do to test whether your theory is consistent or not. And I should point out that these kinds of approaches have been pretty successful in 2D CFT, at least in rational conformal field theory. You have the Moore-Seiberg work and various generalizations of it that you take this program to its logical extreme, at least for rational conformal field theory in 2D, and maybe it's possible to update those ideas in higher dimensions and do things that way. But another way to try to do it is to just start from some theory and turn on some wacky theory, turn on some coupling, and then see if you get something strange in the IR. So this has some benefits. One benefit is that if you start from something that's a good theory, you're necessarily going to end up with something that's a good theory. But it also, of course, has drawbacks, which is that the renormalization group is probably the hardest thing that we can do in quantum field theory, and you're never exactly sure that what you're studying in the infrared is what you think you're studying. So if we try to take this approach, at least to try to push the boundary of what might be possible without guaranteeing the existence of something exotic, but at least trying to push the boundary of how we construct these theories, then it's useful to keep in mind that the n equals 4 supersymmetry in such an RG construction would have to be accidental. And the reason it has to be accidental is that obviously if you start from an n equals 4 Lagrangian and you preserve n equals 4 supersymmetry, the only thing you can do is turn on vacuum expectation values, and you'll just end up with another n equals 4 theory that's Lagrangian in the IR. So before describing a bit more about what you could possibly do to try to engineer these theories via the RG flow, let me just point out that, let me just explain a little bit more how accidental symmetries work. So this is something that I'm sure everybody knows. But the basic idea is that you start from some theory in the UV, you deform it by turning on some relevant deformation, and then when you study the correlation functions in the theory at long distance, they effectively are captured by the correlation functions of some infrared CFT, plus, I'm assuming the theory is not gapped, plus some irrelevant deformations. So these O tilde I are some operators that are irrelevant. These lambda tilde I are irrelevant couplings. And so these lambda tilde I go to 0 as we flow to the infrared. Now, in general, it's quite clear that these operators will usually break symmetries of the infrared theory. I mean, unless you've done some kind of tuning, essentially, in the space of theories. So since these things, if these couplings break some symmetries of the IR CFT, then as they're renormalized to 0, you find emergent symmetries in the IR. And these are things that were not present in the UV description of the theory. So this kind of idea, focusing on the case where these lambdas are giving you accidental supersymmetries, has been studied a lot in the last, 20, 30 years. So here's just a smattering of some of the results. So there's been a lot of condensed matter work showing in 3 dimensions enhancement from n equals 0 to n equals 1 and n equals 2 supersymmetry. Scott Thomas also gave a talk about that at KITP, I think, before many of these papers were written. But anyway, there's also very famously ABJM showed RG flows where they found enhancement from n equals 3 to n equals 6 or n equals 8. Also recently, Gaiotto and friends and Benini and friends have found some interesting examples of n equals 1 to n equals 2 enhancement in 3 dimensions. Finally, in 4 dimensions, there are a lot of examples of n equals 1 to n equals 2 enhancement that have received a lot of attention in the last, 3 years. So Mariyoshi and Sung kicked this off, and then various people have contributed a lot to this, including Simone and others. And there are also actually a couple of examples in papers by Argyris and Martone and collaborators of enhancements of flows from n equals 2 to n equals 4. So how can you hope to construct these theories? So there are 2 things that you can do. You can either turn on a vacuum expectation value, you can turn on a relevant deformation, or you could do a combination of both. If you turn on a vacuum expectation value, as I explained, the UV theory really should have less than n equals 4 supersymmetry, unless you're starting from something that's already exotic. So you could start from something with n equals 3 supersymmetry, 2, 1, or 0. I honestly don't have anything useful to say about this option, but it might be a very interesting thing to do. The other thing you can do is you can just turn on a relevant deformation. So in this case, the theory should be either n equals 2, n equals 1, or n equals 0, basically because n equals 3 theories don't have relevant deformations that preserve n equals 3. They would break to n equals 2 or some smaller amount of supersymmetry, so I would count those as part of these theories. So obviously n equals 0 is very interesting, but at least from my set of abilities, hopeless. And the n equals 1 examples is also interesting, but I find the space of those theories too mind-boggling. So the n equals 2 set is also very nice because, as I'll explain, there are still a lot of very interesting and very exotic and very poorly understood n equals 2 theories, even though that space is more limited than the set of n equals 1 theories. Any questions? Okay, so the UV starting point for the n equals 2 theories that we'll construct is something quite similar to what Shlomo discussed. So we take the an minus 1, 2, 0 theory on a very simple Riemann surface, just the CP1. The only complication, so this is the an minus 1, 2, 0 theory. The only complication, the only interesting feature of this surface really is some puncture, which is called an irregular puncture that I'll get to in a moment, which sits at some point, let's call it z equals infinity, on this CP1. So these set of singularities are actually very interesting, and really I think it's fair to say that our understanding of them is mostly due to groundbreaking work of Dan Xi and also very nice work of Bonelli, Marioschi, and Tanzini. These singularities are very interesting because when you do a twisted compactification of the an minus 1, 2, 0 theory on this kind of surface, you get, in general, 4D CFTs that have n equals 2 supersymmetry and have non-integer chiral operators. So they're more general than the kind of theories that Gaiotto considered it in that way. And also there's some evidence that all the theories that Gaiotto constructed can actually also be constructed just from these kinds of setups with just an irregular singularity. But of course you see that geometrically understanding things like marginal deformations and other such things is much harder here because all we have is sort of one point, and it's not clear geometrically really how to understand this very well. But the point is that understanding this space of punctures and the possible set of punctures you can put on CP1 while preserving this amount of supersymmetry is still an interesting and quasi-open question, and it results in probably a lot of very interesting theories that are not yet known. So just as in Shlomo's talk, to gain some handle on this theory, it's useful to first compactify on S1 to get some kind of, so you imagine you have an S1, and you have also this Riemann surface, this CP1, and you imagine, let's say, making this S1 very small. Then effectively what you get is you get a 5D maximally symmetric Yang-Mills theory, and this twist that you have to do along the Riemann surface ensures that part of that vector multiplet becomes a 1, 0 form on the Riemann surface, often called the Higgs field. And the Higgs field has this interesting expansion on the CP1. So it contains a bunch of singular terms. These terms that I've written here are all singular. And ultimately, in 4 dimensions, they encode coupling constants. And then in these ellipses are an infinite number of terms in general that describe aspects of the vacuum moduli space. So T here are traceless n by n diagonal matrices. And this number L is an integer greater than 1. Otherwise, you're back in the situation with a regular puncture, which is not so exciting. So this profile, this field profile, along with a gauge field on this curve, forms part of a solution of Hitchin's equations. And when you compactify the 5D theory on this Riemann surface, you get a 3-dimensional theory. And basically, the parameter space of these solutions describes the moduli space of the 3D theory, of the mirror of the 3D theory that you would get by taking the 6D theory, first compactifying on the Riemann surface, and then compactifying on a circle. So by mirror symmetry, this gives you essentially the Coulomb branch of the direct reduction, and from the fact that Coulomb branch is some kind of base of the corresponding fibration, some information about the 4D Coulomb branch as well. So for example, the Seiberg-Witten curve comes from the spectral curve of the so-called Hitchin system. It's just this determinant here. So just like in Alberto Lerda's talk, secretly there are Levy subgroups at work here, but I won't tell you about them. But basically, you have these singular terms, these matrices, can kind of obviously be put into correspondence with some Young diagrams. So the Young diagrams encode the degeneracies of the different matrices. So the Ti, for example, is going to be one of these singular terms, and it will have some, let's say, ni, 1 block of degenerate eigenvalues, then an ni, 2 block of degenerate eigenvalues, etc. And this, of course, the sum of these degeneracies has to be n, where n is the n of the an minus 1 theory. So when we have columns of height greater than 1, so when some of these n's are bigger than 1, we get a degeneracy, and this is what's called the type 3 Argyris-Douglas or generalized Argyris-Douglas theory, if you want. These theories are actually extremely interesting. They're still not completely understood. They have a bunch of phenomena that probably occur in them that that I don't think people appreciate yet. And also, most of these theories, where you have these kinds of degeneracies, don't have a Lagrangian in the sense of Mariyoshi and Song. So in our talk here, the particular set of theories that will be involved in supersymmetry enhancement, the claim is that the particular set of theories that will be involved in supersymmetry enhancement will be the theories that are specified by these three Young diagrams in equation 7. So y1, 0 really means y1 equals y0 equals blah, blah, blah. So y1 corresponds to T1, so the third order pole for the Higgs field. Then y0 corresponds to the second order pole for the Higgs field. And then y minus 1 corresponds to the first order pole. I should point out that for those of you who know a bit more about this, this y minus 1 just encodes the mass parameters, so things that are related to flavor symmetries of the four-dimensional n equals 2 theory. So basically what you do is you have k columns, k1 equals k0 columns in y1 and y0 respectively of height n, and then the mass parameters further partition these columns into an additional one where you take the last n and you divide it into n minus 1 and 1. So this number k, which is the same thing as k1 and k0, is related to n of the an minus 1 theory in this way. N is equal to little n that appears here times k. And there's a basic constraint that this n should be bigger than or equal to 2, and k should be bigger than or equal to 3. So at least for my taste, this kind of description in terms of a Hitchin system is quite abstract. So I prefer to have kind of a more pedestrian view. We can construct kind of the simplest possible class of these theories by taking little n equals 2 and k, or k1 and k0, equals 3, in which case we have these three Young diagrams specifying the singular limit of this Higgs field, and therefore characterizing the four-dimensional theory. So this description is a bit abstract, but there's also a very nice way to obtain it, just involving dualities from well-known superconformal field theories. So you can start, for example, with two copies of the so-called A1-D4 theory. So what's the A1-D4 theory? It's a theory that was discovered in 1995 by Argyris and friends, and what it is it's just the theory that sits, or a theory that sits at a singular point on the Coulomb branch of the usual SU2 super QCD with three flavors. It has an SU3 flavor symmetry, and you can diagonally gauge that SU3 symmetry diagonally for two copies of A1-D4, and you could add three fundamental flavors, and you can convince yourself with some calculation that this beta function, the resulting beta function, vanishes, and this is itself a superconformal field theory built from some strongly interacting blocks.
What's the residual symmetry?
U3, yeah. So basically, you lose all the symmetry from these Argyris-Douglas theories, and you just have the U3 from the matter, from the weakly coupled matter. Now, if you go to infinite coupling in the exactly marginal space, you might expect, and it turns out to be true, that there's a dual weakly coupled description of SU2. So the SU2 gauge coupling becomes weakly coupled when you take the SU3 coupling to infinity. But the reason I put weakly coupled in quotation marks is, of course, that these blocks, these red blocks, are themselves strongly coupled isolated theories, but they're coupled at least weakly to some gauge group. So for those of you who know about Argyris-Seiberg duality, this is very reminiscent of Argyris-Seiberg duality, where you basically replace half the fundamental flavors by A1-D4 theories. And then this, again, looks a bit like the hypermultiple that appears on the SU2 side of that duality, and T3 3/2 is going to be essentially some kind of freer version of the E6 theory. So T3 3/2 is another name for this theory in equation 8. So in particular, without ever discussing Hitchin systems or AN-1 or 2, 0 or whatever, just from simple dualities, you can construct this theory. So it exists. It's not a figment of someone's imagination. And it's basically this theory that lives, that's described in equation 8. So this theory has n equals 2 generators of chiral ring generators, so I mean Coulomb branch operators, if you want, of dimensions 3 and 3/2. So this 3/2 already ensures that there's no 4D n equals 2 Lagrangian, because any such theory obviously has to have integer dimensional chiral operators. Also, moreover, it doesn't have a Lagrangian in the sense of these accidental n equals 1 Lagrangians of Mariyoshi and Song. So you can imagine that this theory is not completely trivial to understand. And in fact, the Hitchin description sort of hides some mass parameter of this theory. So in a paper last year, we kind of analyzed this theory a bit more carefully, and we used this chiral algebra procedure that I mentioned that Rostelli and Beam and collaborators came up with. So there's some sector of operators in 4D n equals 2 theories, the so-called Schur operators, that are isomorphic to a two-dimensional chiral algebra. And using that fact, and using essentially imposing Jacobi identities amongst generators, so some kind of bootstrap procedure for the chiral algebra, we showed that this T3 3/2 theory actually splits up into a free hypermultiplet and some interacting piece, Tx, which is irreducible. So again, this Tx is some non-Lagrangian piece, and it turns out to have flavor symmetry SU2 times SU3. For anyone who cares, if you think of it as an n equals 1 theory, it has symmetry SU3 times SU2 times U1. I don't know if anyone cares anymore. But this other hypermultiplet has flavor symmetry SU2. And so this combined combination has flavor symmetry SU2 squared times SU3. So one thing to point out is that this chiral algebra procedure and some simple anomaly matching discussion lead us to the first sort of connection with n equals 4, which is that the SU2 flavor symmetry of Tx turns out has a Witten anomaly. Okay, that follows just from this construction that we got from the chiral algebra and from anomaly matching. So this is sort of the first indication that there is some kind of n equals 4 supersymmetry, perhaps hidden somewhere. Now, it's actually a bit more interesting to push on further and to construct the Schur index. So Luigi discussed the Schur index yesterday, or the day before, I think. And so I'm not going to really remind you of what it is, but roughly speaking, it's a version of the Witten index, and it counts operators, some protected operators, in 4D n equals 2 theories. And you find some, you express the Schur index as some series, some power series in some fugacity Q. This Q basically encodes the SU2R weight and scaling dimension in 4 dimensions of the corresponding operator. And you get some list of operators. And we were able, after bootstrapping the chiral algebra, to magically compute this full sum of operators. And what it is it's a sum, it's an infinite sum. And it has various pieces. So these CHs are characters of affine Kac-Moody SU2 at level -2. And these characters are characters of affine SU3 at level -3. And these things here are some plathistic exponentials that essentially add back in operators that are missing in critical level affine Kac-Moody modules. So this infinite sum turns out to describe the Schur sector of this theory here. Now, what's interesting is that this is extremely closely related to the Schur index of the T2 theory. So the T2 theory is a free theory. It's just this simple 3-punctured sphere in the A1 theory. And it's just a collection of 8 half hypermultiplets, essentially. But through some very nice rewriting, actually, that was this idea of rewriting it in terms of rewriting TN theories in terms of characters like this is actually due to Lemos and Pillars. So they had a very nice paper where they rewrote TN indices in this way. And when you do that, you find that the T2 index is remarkably similar to the Tx index. In particular, you sum, in this case, over affine Kac-Moody characters that are related to each of the 3 punctures. So they're all SU2 at the critical level, at level -2. And you have fugacities, x, y, and z for the different SU2 punctures. And again, you have some plathistic exponential. And remarkably, this formula is basically the same as this formula, except instead of summing over diagonal SU2 representations, here you basically sum over diagonal SU3 representation and SU2 representation. So these lambda, I should say, these are just Dinkin labels of the corresponding primary in this module. So these are labeled lambda, and these are labeled lambda. So instead of summing over diagonal characters of SU2, you sum over diagonal characters of SU2 and SU3. You have the same number of fugacities, everything. And remarkably, also these structure constants that sit in front, these things that you add back in to the critical level modules, are exactly the same. Yeah, so that's related to the fact that there's a Higgs branch operator. In T2, as you know, the simplest Higgs branch operator is a hypermultiplet. In the Tx theory, the simplest Higgs branch operator is a dimension 3/2 operator. So, I'm certainly not claiming that these things are identical. They're not, obviously, but there is a close correspondence. So T2, as we know, has a very, very simple connection with n equals 4 super Yang-Mills. So in particular, if you take the 3-punctured sphere and you glue 2 of the punctures, then you get a torus with a single puncture. And this is nothing but SU2 n equals 4 super Yang-Mills plus some annoying decoupled hypermultiplet. And so what you might guess from this structure is that since here all you have to do to get n equals 4 is to dynamically gauge SU2 times SU2, you might guess that to get n equals 4 in this context, what you should do is you should introduce some dynamical gauge field for SU3. So that strategy is not quite right, but it's basically right. Instead, we're going to introduce some background gauge field for SU3 and turn on some VEVs for it, so some masses. So, but to proceed, one very useful thing to do is to take this expression and compute the q goes to 1 limit. So if you think about the index as some kind of S1 times S3 partition function, then taking this q goes to 1 limit corresponds to taking the S1 to 0 radius, and you reproduce then some kind of S3 partition function. And magically, I mean, if you compute this and you have a PhD student who's as good as Zoltan, you can show that that partition function is just equivalent to this quiver. Where this is an n equals 4 3D theory, so this is a U2 gauge node in 3D n equals 4. This loop here is an n equals 4 adjoint hypermultiplet of U2, so it contains a triplet and a 1 of the SU2, and then these are 3 fundamental flavors. So just as a quick sanity check, we said that this TX theory had SU2 times SU3, the T3 3/2 theory had SU2 times SU2 times SU3 flavor symmetry. So one SU2 obviously comes from the adjoint that's neutral under everything. That's just a free field. So that has, again, as in 4 dimensions, flavor symmetry SU2. Then the triplet of adjoint fields here are, again, they transform actually as 3 copies of something charged under SU2. And this is just the 3-dimensional version of this, the fact that there's a Witten anomaly for the corresponding SU2 symmetry. And finally, there's a triplet of fundamentals. So these guys furnish the SU3 symmetry of the 4-dimensional theory. So I emphasize the 4-dimensional theory manifestly does not have an n equals 2 Lagrangian. That just follows again from the fact that any Lagrangian with 4D n equals 2 must have only integer dimensional chiral operators. Yet, when we reduce the theory on S1, we do find a Lagrangian. But that does not in any way say anything about a 4-dimensional Lagrangian. So turning on SU3 masses, there are some asterisks here that I won't bother telling you about, but if you ask, I can tell you afterwards. You'll always flow to the SCFT that you get by starting from the U2 n equals 8 theory in 3 dimensions and flowing to the IR. So this is an n equals 8 3D theory. So in other words, at least if you take the q goes to 1 limit, you flow to the same 3D n equals 8 theory that you flow to when you put the U2 the U2 4D n equals 4 super Yang-Mills theory on a circle. But again, just because there's a Lagrangian in 3 dimensions certainly does not mean that there's a Lagrangian in 4 dimensions. Yeah.
So can you ask again about the force 3D limit?
Yeah.
For the Schur index, you try to take a circle to 0.
Yeah.
It doesn't mean anything. It doesn't reproduce the 3-dimensional partition.
It does reproduce the 3-dimensional partition function up to a divergent piece.
I thought you had to start with more general capacities.
No. The Schur index absolutely gives you partition functions in 3D. There is some divergent piece that encodes the anomalies, but you get the 3D partition function on the nose. So this has been checked in infinitely many examples. I mean, I could give you a list. We could be here all day long.
What kind of partition function?
S3 partition function. So you have some prefactor which has generally some essential singularity, which you remove. So that's what this squiggly sign means. You do divide out by something, but you get the S3 partition function, and you get it on the nose. This is known, I mean, in many papers. I mean, many examples on the round sphere. Yeah. Okay. So what do we have so far? So what we have is we have this diagram here. So this is a diagram for general n and general k. But the example that I told you about so far has n equals 2 and k equals 3. So, and TUV 4D is this T3 3/2 theory specified by the Young diagrams I explained, and its reduction on a circle leads to this quiver with n equals 2 and k equals 3. By turning on mass terms of this theory, we flow to the 3D n equals 8 theory where n equals 2 there. So we have some diagram, at least, where we preserve 8 Poincare supercharges by reducing on S1, and then we, again, flow from UV to IR by turning on some SU3 mass terms, and we have this flow here. Now, the point is, one point is that this diagram commutes. And the reason this diagram commutes is that when we put a 4-dimensional theory on a circle, there are not really any kind of non-perturbative things that we could contemplate worrying about when we go to 3 dimensions. Said, so for example, one way to assure yourself of that is that in 4D n equals 2, flavor symmetries are non-anomalous. That just follows from the OPE of 4D n equals 2. And so, you don't need the same kind of terms that appear when you reduce 4D n equals 1 theories on a circle. Moreover, these mass terms that you turn on, since they respect 3D n equals 4, they also don't lead to Chern-Simons terms. So, obviously, if you had to worry about Chern-Simons terms in 3 dimensions, you probably couldn't talk about a commuting diagram because you'd need some analog of Chern-Simons terms in 4D. But since these things are true, basically since you have sufficient supersymmetry, this diagram commutes. So I could first go, instead of turning on mass terms in 3 dimensions, I could first turn on holomorphic moment maps that are related by n equals 2 supersymmetry to the SU3 symmetry in our case, or more generally the SUK symmetry, as I'll get to in a bit. You could first do that, flow to the IR, and then consider the reduction of this theory on a circle. Any questions? Yeah. Oh, good. Yeah, so actually I never actually discussed the mirror explicitly. So these computations were just actually about the direct reduction. I bypassed the discussion of the mirror altogether. Exactly. You can also, so Dan Shi has some very nice papers where he basically generalized some work of Balch and other people in Witten and other people, and you can compute also from his prescription the mirror if you want, and you end up with something that's mirror to what we have. Oh, well, so this, you're asking about this. So, well, in the case of n equals 2 and n equals, so in the case of this theory here, well, the mirror, if you're asking about the mirror, I mean, you have something like this. Yeah. In general, there's a K gone, I think. Sorry, yeah. 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 This flow
goes to an immediate Chern-Kuiper.
What does this flow mean?
Yeah.
It just means that in this flow here, oops, I'm going way too far ahead. It just means that in this flow here, all I've done is I've put the theory on a circle. I haven't turned on any mass parameters. So this direction is compactifying on S1. This direction is turning on mass parameters. Yeah. I suppose so, yeah. So one natural question, of course, is what happens just along this top arrow? So in other words, in the limit where we take this circle to infinity. So the question is, what's this IR theory, TIR 4D, when we take R to infinity? So one natural question is, well, there are two at least that pop to my mind. One is the IR theory in this limit 4D n equals 4? Well, we've seen that this theory is certainly 3D n equals 8. And is it U2 n equals 4 super Yang-Mills or not? So just a couple of comments before trying to look into that a little bit further. So these deformations make it clear that Tx, so remember this TuV4D is some hypermultiplet plus some interacting piece Tx, which has a Witten anomaly for its SU2 factor. So the fact that we turn on SU3 moment maps in going from the UV to the IR in 4 dimensions guarantees that this Witten anomaly is preserved. So whatever TIR 4D is, it certainly has the Witten anomaly of the UV theory. So that's at least one good thing if you're trying to match this on to n equals 4. Another comment is just that the existence of a 3-dimensional Lagrangian doesn't really answer these two questions. And the reason is just, again, that this theory certainly had a 3D n equals 4 Lagrangian, but this one manifestly did not. So a priori, there's no reason why this should have a Lagrangian in 4 dimensions either. And also, it doesn't tell you anything, unfortunately, about accidental symmetry, because you can presumably have accidental symmetries even if you have a Lagrangian in lower dimensions. So to gain some understanding, one thing that we did, and we're now in the process of trying to complete this picture with some additional calculations, also with Lotte Hollands. But what we did so far to study this theory a little bit more in 4 dimensions was to just take a look at the Seiberg-Witten curve of the IR theory. So the UV theory, so what's the strategy going to be? So we're starting from some Hitchin system, some theory that has a description in terms of a Hitchin system. So therefore, it is guaranteed to have a Seiberg-Witten curve because you can just take the corresponding spectral curve and get the Seiberg-Witten curve. So in our case, with the Young tableau or Young diagrams that we described before, the degeneracies 2, 2, 2 show up in this leading third-order pole. You see these 2 eigenvalues are degenerate, these 2 are degenerate, these 2 are degenerate. Then again, the second Young diagram is 2, 2, 2, so these things are degenerate. The third Young diagram, which describes the mass parameters, are, you have 2, 2, 1, 1, where M1 and M2 are going to turn out to be SU3 mass parameters, and M3 is an SU2 mass parameter. And then there are subleading non-singular pieces in the z goes to infinity limit that eventually correspond to VEVs that give rise to VEVs for the Coulomb branch operators. So you can write the curve. It's a god-awful mess. I mean, I'm not going to really go into excruciating detail about it, except to tell you that there are vacuum expectation values that appear. So as is standard in the curve, since the curve is an effective description, it's not describing the CFT itself. It's instead describing an effective theory of the UV CFT on its Coulomb branch. What we have is we have some operator, some VEV, for a corresponding chiral operator, the dimension 3 chiral ring generator in the UV theory. Then we have, again, some VEV U1 for the dimension 3 halves operator. And as is typically standard, relevant deformations, the mass parameters M1, M2, and M3, appear in this curve, as does the dimension half coupling B. So the dimension half coupling is just the dimension of the coupling in the prepotential that you get by turning on the dimension 3 halves relevant operator in the UV theory. Now, why do I bother telling you about the curve? So the curve itself is not a UV description, and actually part of the point is that the curve can potentially hide things about the UV theory. For example, I don't know of a general reason why, if you have a marginal deformation of a UV theory, or even some relevant deformations, why it necessarily has to appear in the curve, because the curve is an infrared description. But in any case, we're going to take this curve, and what we try to do is we try to carve then the curve of the carve out the curve in the Coulomb branch of the corresponding infrared theory along this flow. So this curve I've just shown you is the curve corresponding to T4D UV, and out of that you try to carve a curve for the corresponding infrared theory in 4D. So this is a somewhat indirect way to study these theories, and obviously not the best way to do it, but it's what we've done so far. So to do that, what you do is you take what's called a scaling limit. So you take some RG scale, some cutoff, or whatever you want to call it, M, and you take the limit where you send that cutoff to infinity, and you assign the different terms in the curve different scalings with that M. Okay? So the only consistent scaling limits that we've been able to find up to isomorphisms that I won't bother telling you about here, but I can tell you about if you want privately or in discussions afterwards, this is the scaling limit that we've found. Now here, the x and z, little x and little z, are the coordinates on the UV curve. And then the capital X and capital Z are coordinates on the IR curve. They're good coordinates in the sense that they don't scale with this M goes to infinity guy. B, you can see, becomes something that looks naively marginal in the infrared. So it starts its life as something dimension half in the UV. You assign it a scaling dimension a half sort of term here. And then what remains is just some dimensionless coupling Q. So you might think that it becomes something marginal in the infrared. Similarly, the U2, the VEV of dimension 3 in the UV, it scales with m to the first power and times u. And so this whole u has dimension 2 if u2 has dimension 3. And so by this kind of spurion analysis, you assign scaling dimensions to the IR theory, and you try to find the most general possible scaling limit that you can. And this is what we've, I don't have a Bourbaki proof that this is the only possible scaling limit up to isomorphisms, but as best we can tell, that's the case. So taking this limit gives you something interesting. It gives you essentially a curve which looks just like the SU2n equals 4 curve tuned to a cusp. So you have some u of dimension 2, which is good because you expect, at least in any theory that has an exactly marginal coupling, you expect that you can give a VEV to the conformal primary related to the marginal coupling. So it's good news that we have u here. But you see something interesting. So usually the curve, the n equals 4 curve, away from a cusp, this quartic polynomial here should have non-degenerate roots. But you see, the naively marginal coupling that we have from the Hitchens system, this Q, actually doesn't correspond to a marginal coupling in the infrared. So when you tune Q, you still stay at a cusp, which is rather unusual, because usually what happens when you have an n equals 4 Lagrangian is you have a gauge coupling, and you change the gauge coupling, and you go away from a cusp, and the curve becomes non-degenerate. And also, via the Higgs mechanism, the W bosons get masses that involve the gauge coupling. But here, you can see that whatever, there's going to be obviously a massless coordinate on the moduli space, but then there'll be W bosons that have a mass that's independent of the gauge coupling, which looks very, very peculiar. So one interpretation might be that these things are just effective degrees of freedom on the n equals 4 Coulomb branch, but are not actually related to things that really exist in the UV theory. But so what are the possible explanations for this fact that the naively marginal parameter that usually remains or is related to something marginal on the Coulomb branch is actually irrelevant here? So first thing, I just have to give you this caveat that we haven't been able to disprove that there might be a more general scaling limit at play, although, again, I consider that unlikely. The two more likely possibilities are, one, that this four-dimensional theory, we have this flow from TUV 4D, which was this T3, 3/2 theory, to TIR 4D. And in this flow, it might just be that the marginal direction is invisible. Although, in most examples I'm aware of, you can always see this marginal direction. Maybe there's a surprise here, and instead, you should be at some closer fixed point, which I've denoted by some kind of longer wavelength x, where maybe by flowing from some other fixed point t bar, you can see this marginal deformation better, or you can actually see it. So again, here it looks irrelevant in the IR on the Coulomb branch, but here, perhaps from some other fixed point, maybe even an n equals 1 fixed point, it would look actually marginal. A final possibility is that we have something which is more exotic, which would be more interesting, perhaps, or more surprising. And what does this mean? Well, imagine now that this TIR is just some point on some conformal manifold. As I said, usually when you vary a gauge coupling by the Higgs mechanism, the corresponding W bosons get a mass that involves the gauge coupling. Here, that doesn't seem to happen. So one possibility is that marginal directions, all marginal directions that you can go along in the UV conformal manifold. UV, by the way, UV I mean the TIR 4D conformal manifold. There are unfortunately many UVs in IR at play here. But what I mean is that all the marginal deformations, at least naively, this calculation suggests, since the curve remains degenerate, that all marginal deformations in the UV theory become irrelevant in the IR. So all the points here that are related by marginal deformations along the UV conformal manifold just get related to the same point. Any questions? So here, the idea would be that the gauge bosons are just some kind of effective, there's no reason for gauge, just like in Seiberg duality, right? Gauge, different gauge groups appear, they disappear. Here, the same thing would be happening. That's at least the most direct interpretation of this fact. Now, what are some generalizations? Oh, that's okay. So let me give you some generalizations. So this can be generalized a lot. So for example, instead of taking n equals 2, you could take n equals n, and you could take, and then you get these three Young diagrams. And then, yeah, sorry. Yeah.
Can you take this deformation at the level of the Schur index?
So that's something that we're working on, but we've been banging our heads on this for a long time. But I think now we have some kind of progress, but it's not enough to say that. I mean, we have, in some simple examples, we understand how to do it. This example is too complicated so far. But yeah, I don't know. So that would be great. Yeah, yeah. Well, I should say what we have actually is something a bit better, which is, well, it's too preliminary. But what we're looking at essentially is being able to start from the chiral algebra and give a prescription for turning on mass terms, and then relating the UV chiral algebra to the IR chiral algebra, which would have as a side effect the ability to say something about the Schur index. But it involves some weird residues and stuff that need to be worked out. So this theory would correspond to some 4D SCFT, and you can compute the Coulomb branch, the chiral ring generators of this theory, and they're very interesting. So instead of just 3/2 3, you have 3/2 3, 9/2, etc. So they're just multiples of 3/2. They're very reminiscent of what you might imagine in an n equals 4 theory, but now graded in half integers. And again, you can run the same trick. You have an S1 reduction, which is just this. And you can again argue that this diagram commutes, this diagram here commutes, and all the same things happen. And then finally, you can also consider even more rows here. The 4D n equals 2 theory has generators of these dimensions. These are Coulomb branch. Yeah. When I say n equals 2 chiral ring, I always mean operators that are annihilated by the chiral part of n equals 2 superspace. So I never include Higgs branch in that. So you can generalize this by considering Young diagrams that have k columns instead of 3. And then you just get some theory with now this un and this k here. And again, you can look at this diagram and you'll again find some, by the same arguments, obviously it doesn't depend on n and k, that this thing commutes. And you end up in some similar predicament. So, okay, so the conclusion, so what we found is at least some kind of new playground for engineering accidental SUSY enhancement, at least in this n equals 2 and k equals 3 case, which we've checked more carefully than the other ones. It seems that we've constructed a 4D n equals 4 theory without ever discussing free fields. And of course, it's very interesting to try to really figure out, more completely what's actually going on in 4D with some more powerful techniques. And so, yeah, then hopefully, I mean, a pipe dream would be to answer the question at some point if we know everything there is to know about 4D n equals 4 and maybe other maximally symmetric sets of theories. Thanks. He had n equals 4 in the IR. I see.
Starting from n equal 1 without masses, but with partial couplings between the three chiral matrices. I remember you were fine with it.
But so there was was it kind of a perturbative thing where he had some n equals 1? I see. Yeah, so my guess is that there. I see. So I would have to look at it, but my guess is that there it's going to be probably, if it's an n equals 4 theory, it'll probably be super Yang-Mills, right? I mean, I would guess. Yeah. I see. I see.
What's the what are the details of the equal 1 theory? The intensity was n equal 1 with 3 chiral matrices and 1 base matrix.
Yeah, so I think it's probably, is it right to say it's some perturbative RG analysis? Yeah. Yeah. I see. And it's attractive, the n equals 4. I see. Yeah. Yeah.
Where the fact that you asked the question, what is the nature of this for the theory, you are not sure that it will be U2?
Well, I mean, it looks, naively, it looks like it's not U2 n equals 4. I mean, yeah, naively it does not look like it's U2 n equals 4, right? Because this Seiberg-Witten curve has this weird peculiarity. I mean, the only reason that I don't want to come out and declare that it's not U2 n equals 4 is that, well, there's also a possibility that there's just that you might have another fixed point that might show you that marginal deformation, which might just be a gauge coupling, and it might somehow be invisible from this UV fixed point that I started from. That's a logical possibility.
Where do you think this diagram?
Well, it's not an issue of commutativity. I mean, it's just that, when you go from 4D to 3D, different 4D starting points can give the same 3D theory. So, for example, this TUV 4D theory, I've argued, has non-integer chiral operators. Therefore, it doesn't have an n equals 2 Lagrangian in 4D. So this direction can certainly be reached by starting from something non-Lagrangian in 4D. But you could also do something simpler, right? You could just start from this theory. I don't care if it's not asymptotically free in 4D and flow to the same point. So this is a many-to-one map, right? So you can't just go from here backwards. It's not well defined, right?